So hi everyone, welcome to this webinar. So today we are very happy to have Qing Tang from China University of Geosciences in Wuhan. Thank you very much for making it and for accepting to give this talk. So today Qing is going to talk about policy iteration algorithms for mean-field game systems, theory and finite difference methods. Thank you very much again, and the floor is yours.
Okay, thank you very much for the invitation. Okay, my talk is mostly based on some joint works with my friend Fabio Camilli from Rome, Mathieu Laurier here, and Song Jiahao, who is a graduate student of mine in Wuhan. Okay, it's mostly based on these three papers, but I'll be focused on the last one, which is my recent work with my graduate student Jiahao Song. Okay, so just one minute. Okay, so these are the main references. Of course, I cannot list all the relevant references of papers which made very important contributions. For a lot of results, I will just cite the lecture notes of Mathieu Laurier from 2021. Okay, it contains a lot of the classical methods and the results for the numerical analysis of mean field games. Okay, so this is a system I'm going to study. There is a single agent optimal control problem. Okay, and we define the Hamiltonian, and above it's the forward-backward mean field game system. Okay, so the only thing I want to explain is that I use a notation Fm here. F is in this bracket, signifying that I will be focusing on non-local or what is called a global coupling rather than local coupling. Okay, I will also discuss local coupling in my talk, and it has been discussed as well in my paper, but non-local coupling would be the focus. Okay, and I have a backward AGB equation and a forward Fokker-Planck equation. Okay, this is the main setup. Oh, Okay. An important feature of a mean field game is this duality structure. If we linear,
just a quick question. What was Q? There was in Q.
Q is the drift. It's a minus drift. Okay, I put a minus sign here. Q is the control, the policy. Okay.
Q is Q in the state equations. In the state and the Hamilton-Jacobi. Like in the mean field system, it says in Q.
Excuse me.
In the mean field system, like the first system, like 1 and 2, equations 1 and 2. In the end, it says in Q. But this Q
is a domain, I guess. Maybe it's a time space.
The capital Q is a domain. It's a parabolic domain. I'm sorry.
Okay.
It means the domain. Okay, it's the time and space. Okay. That's a capital Q. Okay. The small q is the policy. Okay. Later on, I will have another capital Q, which is a discretized version of the policy. I know it's a bit confusing, but okay. But here, capital Q is just the parabolic domain. Okay. So okay, an important feature is that the linearized AGB equation, this operator is the adjoint to the Fokker-Planck equation operator. That's one can obtain that just by integration by parts. So this is very important both for theoretical analysis and numerical method. Okay. These are the main assumptions. These assumptions are very restrictive. I'm making that just so to introduce my last paper and the algorithm called smooth policy iteration to make sure that my result is does not assume like small capital T, like small time horizon, or making other similar kinds of assumptions. Of course, if I make other assumptions, I do not have to use such a narrow definition of Hamiltonian. Okay. A typical example would just be, the kind of quadratic Hamiltonian at the very end of this page. Okay, and this lemma is going to be used throughout the paper. okay, on the left-hand side, what I'm saying is that, okay, if I have a Hamiltonian, and it's subtracted by, something else, it'll be bounded below by the distance between Q and the optimal control. So HP would be some kind of optimal control, and Q would be some other control. So you can think of it like that. So this is very important to bound two different policies or controls. Well, there's some confusion of terminology, but the control is in feedback form. So I also call it policy. Okay, that's the point. On the right-hand side, I just use some Lipschitz property of the Hamiltonian and the Lagrangian. That's all. Okay. And okay, above, okay, I have two sides bound on two sides of the second derivative of the Hamiltonian just to get the convexity and other things. And I made an additional assumption just to make sure I can get some Bornstein estimate to make sure that the gradient view is uniformly bounded. Okay, that's the point. And I make very assumptions on M0. It's a very smooth density, bounded away from zero. This is important for smooth policy iteration and fictitious play. Okay, as well. Throughout the theoretical analysis, I work on the torus, like just for simplicity. But actually, for numerical examples, sometimes I want to work on other domains. Sometimes it's better to work on the other domains with the numerical simulations, but I will get to that. Okay, and then I introduce mass span distance and the space of probability measures. The important thing is that I use that to define what is called a flat derivative of U. U here is just any function of M. This is called a flat derivative. It's different from the intrinsic derivative, but there are some connections. Okay. And here, if I can define the flat derivative, if F and G are the flat derivative of some other things, capital F and capital G have a potential structure for the coupling terms, then I can understand the mean field gain as a convex optimization problem, what is called a variational mean field gain system. And the important thing here is that, in fact, okay, you see the T0 here. So this is from a paper by Briani and Cadillac. So the important thing is if I have a solution to the mean field gain system, then for any later time T0 greater than 0, MW is also the unique minimizer of GT0. Okay, not only starting from 0, but starting from any T0 between 0 and capital T. So the proof is actually very non-trivial. So it was an important result. Okay.
Sorry, can I ask a quick question?
Sure, of course.
So here's a MW. Okay, so W is basically M times Q, I guess.
Yes.
And
yes.
Is it okay? And Q is equal to basically HP of X gradient U. And
yes.
So here, this pair MW, is it clear that so the last line or the second to last line says that the MW will be the same for any JT0, or for different T0 you might get different MW.
So if you have a solution to the MFG system, which is you get an MW, which is a minimizer from time 0, then the same the restriction of this MW from any time any T0 would also be a minimizer from T0 to capital T. It would not be anything else. It would just be it. And but that was it is not very obvious. It was shown in one paper, on stable solution to mean field games. Okay.
Okay. Thanks.
Okay. And then I make some assumptions on the Lipschitz continuity of F and G, and also on the partial derivatives space partial derivatives of f and g. They are all globally Lipschitz continuous. The measure derivatives are also globally Lipschitz continuous. Okay, these are assumptions made in one paper by Briani and Cadillac. These are strong assumptions, but they are satisfied by many couplings. Okay, if these things are Lipschitz, I can derive the following result. Okay, just by using the flat derivative, the definition of flat derivative. I have the following results. On the right-hand side, I use the Wasserstein distance, but of course, if M is a probability measure and a smooth density. Okay, if it is also smooth density, then I can bind the right-hand side, the Wasserstein distance, also by some stronger norms of functions, like spaces, norms for the spaces of continuous functions and so on, much stronger norms, which is what I'm going to do. But here I use the Wasserstein distance on the right hand side because it's more natural, it's more obvious, from the structure of Wasserstein derivatives. Okay, now I want to make some remarks of uncouplings between global versus local, which might be confusing sometimes. Okay, example of global couplings is if I make some convolution between L and M. L is a very smooth kernel. Okay, this is a global coupling. And if L is very smooth, I work on a compact domain, then I satisfy all the assumptions I was making in the last page. If I'm working on a compact domain. So I put omega here. I don't use torus here. I use omega here because sometimes it's for some analysis, it's difficult to restrict to torus. It is better to work with some other domains. For example, if you want some symmetric structure, that's why I use an omega here. Okay, and okay, this is a global coupling. For local couplings, I consider a special case. Okay, it's global coupling. Local coupling is kind of a function. Okay, an example would be what I'm showing here. Okay, in general, problem with local coupling at the final condition is not well defined. Okay, so that's why we read in many papers, including the lecture notes of Mathieu Laurier, that if we discuss local coupling, only running cost is defined, not a terminal cost, because even for very simple, there are very simple. No, I would not say simple. I would say very smart counterexamples proposed by Marco Cherent and his co-authors that even for arbitrarily small capital T, you might have non-existent solutions if you use local coupling at the final condition. Okay. There are a lot of papers. There are many papers on weak solutions for mean-field gains with local couplings, and also you can solve these systems by convex optimization method. There is one chapter on this topic in the book by Mathieu Laurier. And the classical solution of mean-field gain with local coupling has been considered Marco Cherent and Goffey in 2022 in one paper based on Bornstein estimate and the joint method. Okay, so, but again, I will be mostly talking about global couplings. Okay, and this is what is called the Latry-Lians monotonicity condition. Well, for the first two lines would be for global coupling, and the third line would be for local coupling. And again, here, for the local coupling, it's kind of obvious if the monotonicity condition is satisfied. For example, M would be monotone, minus M would be anti-monotone, etc. For global coupling, it's kind of delicate. For each concrete case, one actually needs to do some proof. So these have been done in many places in the book by Carmona de la Rue of concrete examples. But in order to show that the coupling is monotone, you also need to consider what exactly is omega, the domain that you're working on. That's why I put the omega here. So it's Okay, I will not go into details here, but these are just some parabolic estimates I'm going to use. These were originally from books by Ledzinskaya, but you know these. It's better to read the recent papers by Marco Chirant and his co-authors, which has presented the more modern forms, which have been applied for MiFID games. Okay, so you have these estimates for the divergence form PDEs. Well, basically the solution is controlled by some terms on the right-hand side and the final condition. You know, you have a Hodel estimate and Sobolev estimate. That's one thing. And for the Fokker-Planck equation, one needs to use the estimate for parabolic equations in divergence forms. What I want to focus on is to say, okay, what is delta M and delta Q? So these estimates are just saying, okay, how much would the M change if you change slightly Q? You know, if the drift or the policy is slightly changed, how much would how do you measure the change in the probability density or the probability measure? I'm mostly working with PDEs here. That's why I use functional spaces. In fact, you can also there's another theory where you can also just use Wasserstein distance for M for measuring the shifting M. Plus, a very important point is that I have a lot of oh, okay, just 1 minute. A lot of constant C here. The important thing is that it is in general you cannot make assumptions on how big C is. It will be good if we can. Okay, but in general, C is just some constants depending on the data of the problem. It's very intractable. You cannot say C is less than 1 or less than 1 over half. We cannot say that, even if we already know the data. So C is a constant which depends on the data of the problem. It does not mean that we can get a very tractable or accurate estimate of C, even if we know the data of the problem. So that's the point, and that is why sometimes it's very hard to get contractions if we want to use a Banach fixed point, because we don't have the suitable constant. Okay. Here are the algorithm. Okay, I start with the policy iteration for HGB equation. Well, for HGB equation, we start with the Q0, and we solve the linearized HGB equation for UN, then we update UN. So that's you know, just two steps, and we can use the parabolic maximal principle to show that with this algorithm, the policy is monotonically improving, in the sense that the value function is monotonically decreasing. Okay, this is a minimization problem. So the value function is monotonically decreasing is a good thing. It's equivalent to say policy is getting better and better. Okay. Well, the next one is okay. So the theory was developed by Simona Caccazzi, Fabio Camilli, and Alessandro Goffi for MiFID games. Basically, what they are doing is this: they add another step. Okay, so first they generate another M probability distribution from the current policy Q, and then they use this policy for, you know, the final term in the HGB equation. So both these equations are linear, so they are at each step they are solving linear problems. Then they have a policy update, and then they generate another probability distribution. So that's what they are doing. Okay, so we can compare. So the policy iteration for MiFID game system is a linearization trick or a linearization method. We can compare that with Newton method, which is another linearization method, which has been widely used for solving MiFID games by Yves Ashtou and Mathieu Laurier. We can make some comparisons. Okay, if we simplify the things and consider local couplings. Okay, well, I should be careful if I say simply things and use local couplings. In many cases, MFGs with local couplings are more difficult to analyze because of regularity issues, difficulty to estimate or to get a Bernstein estimate, etc. But at least in some cases, I would say local coupling makes things easier for construct algorithms. But this is not always true. Okay, but here, okay, it is. Let's consider local couplings, and we have a PD interpretation of solving mean-field gain with Newton method. The current form was presented in my paper with the committee in 2022. So we interpret mean-field gain solving the system, of F. We are trying to find the root of F, and we use Newton method. And so we understand the whole thing as solving some kind of mean-field gain system. But you see, it clearly is different from policy iteration. For example, for the Fokker-Planck part, so this system is much more linearized than the policy iteration method. I would say that. Okay. You probably need to do more work for each iteration, but if you count by the number of iterations you need, Newton method would converge very fast if one starts with good guesses. Okay, but for good guesses, sometimes people use like Mathieu Laurier usually use well, at least I assume some continuation method. For example, starting with a larger viscosity sigma and so on. Okay, but Newton method is very effective if one use some method to condition some initial guess. Okay, well, one issue with Newton method would be that if we have a local coupling, it is fine. But if we have a global coupling, the partial F, partial M term should be replaced by some kind of Wasserstein derivative, and one would need to use some dense matrices. I'm not sure that would make things difficult, but I would say I would assume people prefer not to use dense matrices if they can avoid it. Well, okay. So in the paper of committee, we call policy iteration cosine Newton method, but in some papers on Newton methods, they call Newton method optimistic or optimal policy iteration method. So there are some intimate connections between these two things, but they are not the same. Again, yeah, well, continuing from my comment, so in the paper of Camilli, Carcassi, and Goffi, they assumed F to be a local coupling, a locally uniform coupling. Okay, F. But you can see that there one can extend the theory to global couplings. There are no like intrinsic reasons not that one cannot do this. Of course, the analysis should be different, which I would make some discussion here. But from a theoretical and numerical point of view, policy iteration can be used for global couplings. Okay. Well, if the first thing, if the interactions are small, then we can get a linear rate of convergence for policy iteration, and it's we can show it here. We just get some estimates, and we have extra term on the right hand side. Again, as I said, we cannot control how big C is. We cannot say C is small. It's not a good. It would not be a good assumption. But we can have a C which is independent of theta and eta, which we can use for the constant for the for F and G, which are globally Lipschitz continuous. Okay, and remember that we have some square term at the on the other things. Then we can get a contraction if theta and eta small. Okay, convergence rate is linear. Okay, but there are more details in the paper of me and the Fabio Camilli, mainly because we want to extend to more general cases like local couplings and so on. But this is the main idea. For short time horizon, The method was originally developed by Michael Cherant in 2020, and me, Mathieu Laurier, and so on. We developed it for proving a convergence of policy iteration algorithm if we assume small t, like a short time horizon. Okay, so all these things are done for mean field game with non-separable Hamiltonians, which may develop singularities. But here, let's consider just a simple case. The heuristic idea would just be this: just use some Sobolev embedding, and eventually we get something like this. I can bound the delta u n+1, the next step by the previous step, times the factor c times something. But the point here is that c remains bounded for bounded t, and which means that if I make capital T very small, C will not blow up, or there's a C which will no longer increase if I'm decreasing capital T, which means that I have a contraction. Okay, this would be for the simplest case. With the non-separable Hamiltonians, we need to do other things, dealing with singularities, etc. But the main idea is this one. Okay, let me compare this with a fixed point iteration and fictitious play. Okay, fixed point iteration, start with an M, get a U, and get another M. Okay, if you use a fixed point iteration, it's not linearized because you still need an inner iteration to solve the HEB equation, and it's typically done by Newton method, which is explained by in the paper by Mathieu Laurier in 2021. The Newton method here would be different from using the Newton method for the whole MFG system. Here, even if F is a global coupling, you don't need any dense matrices if you use the Newton method. It is fine. Okay. 1 minute. And okay. Well, another one is the fictitious play, which basically is each time after you updated M, you use some relaxation or some learning rate to get another M bar. And well, this is the classical fictitious play algorithm in game theory and apply to mean field games, which started with a paper by Cadillac and Hadikulu. Mathieu Laurier worked a lot on this and used it for machine learning. I think this fictitious play is one of the main topic in this webinar. So I want to comment a bit on the learning rates. Okay, first of all, we can use a constant learning rate, which is called a relaxation. Okay, it's widely done. Another one is just to use mean. Okay, this is another one. Well, there's a third one, which is okay. We can use a different learning rate, which is we put the larger and larger weights in more recent observations, which would be, which would behave similar to the simple mean or the Cicero mean, but it might speed up the convergence a little bit. Well, there are proofs in other papers, but here just the intuition. If I put more weights in most recent observations, it seems to be better. Okay, then okay. Now I start to develop the two smooth policy iteration algorithms. One is SPI1. It's like this. Okay, first I get a policy, then I start with the policy. I get a distribution, and I solve the HEB equation, linearized. I get a U, then I do a greedy update Q. And then I don't use the Q directly, but well, do some kind of averaging, smoothing to get a Q bar. That's all. It's like fictitious play, but here everything is linearized. So each step I'm solving a linear equation. So it'll be good for finite difference method. Okay. Well, convergence analysis. Okay. The first steps are easy. First step is just saying, the steps are close to each other. Because I did the smoothing, of course, the smooths are close to each other. Well, we have to use some norms, but these are just like technicalities. So these are the easy steps. And also, we can use PDE theory to show that all the M are bounded away from zero, strictly greater than zero by strong parabolic maximum principle. Okay, the difficult point. Okay, let me explain the main difficulty. Okay, so the idea would be to extracting a convergent subsequence of U and M, because I can show it's uniformly bounded with some norms and extract the convergent subsequences. Okay, and the cluster point, limiting point would be solving some forward-backward system. And I want to use the fact that the MFG solution is unique. Then all subsequences of U and Mn would converge to the same limit. Then the whole sequence converges. Okay, this would be the idea, but there's a problem here. So the problem is that we don't know a priori that the limiting point would be solution to the MFG system. Okay, so we have an algorithm. Okay, we have a sequence, and we extracted a subsequence. We cannot know if the limiting point is a solution to the MFG system because we are using a subsequence. That's the key point.
Sorry, would you mind like showing again the algorithm?
Yeah, sure.
I have a quick question. So, yes, in this one. So, okay, so at each iteration, you start with Qn, then you compute mu(n) by solving the. So basically, Mn, sorry, is like the evolution of the population if everyone uses this Q bar M.
Yes.
And then you evaluate this policy. Basically, you get UN. And then you do the policy update, Qn plus 1, but you don't use it immediately. You use the bar version.
Yes.
Okay. And let's see. So if Q is just, so one question I have is like, is it equivalent to do the average over the U as doing it over the Q? So probably in general, it's not, right? If Q is just minus gradient U, like if you take the linear quadratic case, Q is equal to minus gradient U, then averaging Q is like averaging U, basically. But in general, it's not equivalent, right?
Yeah, I agree. Yes. Yeah.
Okay.
In that particular case, I think so. Yeah.
And if you get, and then about what you raised, like the question you raised, if you get a limit point. So if you get a limit point, you get M star U star, and you know that they solve. So why are you not sure that they are solution to the meaningful game system? Because
because I'm okay. That's a key point. Because I extracted a subsequence. So okay, I have a that's my next line. Okay, so let's see. So like let's use a simple updating rule. Okay, just the average, simple average. So it's just a Cicero mean. If Qn converges, then the mean of Qn would converge to the same limit. That's just the Cicero mean theorem, which is trivial, right? But the problem is that we do not know if Qn convergence or Un Mn convergence. We extracted a subsequence. So if I don't know if a sequence is converging, I extracted a subsequence. Then I cannot be sure. A subsequence of the mean would also be converging to the same limit. So there's a chicken and egg problem.
So could it be, for example, that the solution keeps alternating between two solutions? I mean, the sequence keeps alternating between two solutions, and when you extract a subsequence, it converges, but actually it's not the solution of the mean-field game system because it is solving based on the previous iterate, which is not the same as the current one, something like this.
Yeah. So well, exactly. So basically, well, but basically, when I say extract a subsequence, that's like kind of a theoretical analysis from theoretical point of view.
Sure. Yeah.
but basically, but the whole point is that if I extract a subsequence and have a limit point, it will not. It might not be the solution to the MFG system. I think there's a question. I don't know how to.
I think Carlos has a question. Yeah.
Once you have finished, but my question is very related to that. I didn't want to interrupt you. This is why I raised my hand.
Okay.
Just if you assume that you add also monotonicity in, or can you put some extra assumptions to limit this case? Okay, maybe the alternating or like the multiple solutions that you can. I can understand that if you have like multiple solutions to the MFG game, then you might oscillate and happens what Mathieu says, that you have two sequence and you go to different points. But if you have like monotonicity or some extra assumptions, can you rule out these cases?
Okay. I think what you're referring to is not it's not the same thing as what Mathieu was saying. First of all, let's assume the MFG only has a unique solution. Okay, if it has a multiple solution, that's another thing. Well, I think what Mathieu was saying is that maybe we can have a subsequence. Okay, which converges to something, which converges, but it's not converging to the solution of the mean field gain system, but something else. And we can have another subsequence which converges something else, which is entirely possible. But my point is that, okay, there's a main logic that people are trying to use is to say, I have a uniformly bounded sequence. I can extract the convergent subsequences. If there's only one possible limiting point, then the whole sequence will converge. And this is a typical idea used in viscosity solutions for HEB equations and so on. And this is what I want to use here. But I do not know if all the subsequences have a unique limit point, because their limit point might not be solution to the MFG system. That's the point. You see that? So if I know the MFG system can only have a unique solution, it is not very useful here. I still cannot show that the UN and all the subsequences had the same limiting point. Okay, that's the point. Please let me go to my next slides, and it will be more clear. So, so then the key thing would be to show that Qn and Q bar n converge to 0 uniformly on Q. And this is why we need a potential structure of the MFG system, and that's the real issue here. So this is the same thing that people did in the fictitious play paper, for example, in the paper of Cadillac and Halikulu, and also I believe the paper of Mathieu Laurier on machine learning. Well, it's not the same, but something similar. To use some extra reasonings, complicated reasoning. So I spent a lot of time trying to do things without this. Okay, but eventually I realized why we need this. So I followed the mainstream. Okay. Okay, so the key would be to show Qn and Q bar n converge to 0 uniformly on Q. If this happens, then the limiting point would actually be a solution to the MFG system, and everything is fine. I hope you agree with me on this point, but if you don't, please let me know. I can explain in more detail. Okay, and the next lemma was due to the fictitious play paper by Cadillac and Halikulu. Well, this is a result which allows to use the get convergence without using contraction fixed point. So it was explained in the survey paper by Mathieu Laurier on learning mean field games that sometimes use contraction could be a problem. That it's difficult to get a quantitative estimate, which is exactly the same thing which I explained here. I have a constant C. I cannot assume how big C is, and so on. I can constrain it if I assume like small time horizon and so on. But what if I don't? Okay, I want to do general results. Then what I could do is to not use contraction fixed point, but use the following lemma. which was proved in the previous, in the literature. So this is the mathematical analysis result. Okay. Oh, well, the key steps for convergence is, okay, I have a delta U and delta M, then I use the convexity of L. Then I have a, I can just consider the PDE for delta U and delta M, and I can derive the following bound by using the property of Hamiltonian, which I described earlier. Okay, then I multiply both sides by M. The key thing is to observe there's some kind of duality structure. I can integration by parts, and I have something like this. It's a bit complicated, but as soon as you look at it more carefully, you see you're almost there to telescope. The only two terms that you cannot telescope is the blue terms. This is why you need to use the potential structure or the potential assumption. Maybe there are other assumptions to replace the potential assumption. I hope there are, but I'll be happy to know or to revise it. But at least if you have assumed the potential structure, then you can have the following estimate, and then you are ready to telescope. So if I define an as this one, I can telescope and I have the following estimates, and then I know that this sequence is convergent. I have a convergent sequence, and then I know an tends to 0 from the previous lemma. I'm sorry, I did not write down all the details, but I'm just using this lemma that I know that an tends to 0, and I know that m is bounded away from 0. I can get that HP minus Q bar n converges uniformly to 0 on Q. And that's the whole thing. I've shown this. Okay, Qn minus Q bar n converges to 0 uniformly on Q. And well, I can show, I omit the rest of the steps, but basically I can show the convergence of the SPI1 algorithm. For the second algorithm, well, it's slightly different, but almost the same. SPI2. Okay, I have a guess of Q. I derive M from the Fokker-Planck equation, and then I do some smoothing. But what I do is that I have Q and M. I do some smoothing on M and the flux W. Okay, well, you can think of it as some kind of averaging, and then I divide W bar by M bar to derive some kind of Q hat. So it's not Q bar. I run out of notations, so I have to use Q hat. And then I use Q hat. I evaluate the Q hat to get a UN. Then I get a greedy update Q, and then I use the greedy update Q to solve Fokker-Planck equation. So the method is similar to the previous algorithm, but it's not the same as you can see. It's not exactly the same. So why I was doing this? Because I read the paper for Mathieu Larrier and saw what he was doing with machine learning and so on. And he talks about averaging policy or smoothing the policy, but it's not exactly averaging. So I was trying to guess what he was doing. So here, if we interpret the Q hat, this is the Q hat, the policy which would generate M bar. Well, I think that's a lot of people are doing with machine learning. For example, if you train a neural network, which would generate the average distribution M bar. Here, we don't have a neural network or anything. We just write a PDE with a Q hat, which generates M bar. And the key is to show that Qn and Q hat n are close. It's the same thing as a previous algorithm. If we show they are close, we are fine. And the only difference is that from the previous proof is here we don't use the convexity of L, but we use the joint convexity of W and M. This joint convexity structure is widely used in variational mean field games and optimal transport. It's a classical result. And, okay, I just have to replace the a bit the calculation and following exactly the steps of the previous theorem and integration by part and so on. That's that's the convergence of SPI1 and SPI2, all the main points. The convergence was shown based on the assumption that there's a unique solution to the MFG system. Okay, in the paper I was using the monotonicity condition to say there's a unique solution. But I think there are other assumptions to be made, which could be made to get uniqueness. But okay. Is that clear? Do you think I should explain anything more, or if it's fine, I will just go to the next section. Okay. I will just. Okay. Okay. The next section is stable solution. Okay. What if you have multiple solutions to the MFG system? Okay. There could be a solution. A minimizer would be a stable solution, which means that okay, if M and U is a stable solution, then for this minimizing. For this linearized PDE, you only have a trivial solution. It's the definition of stable solution. And the key estimate we will use was a lemma from.
I'm sorry. Can you I missed the definition of a stable solution. Can you explain again? Sorry.
So if UM is a solution to the MFG with initial condition T0 and M0, starting from any T0 between 0 and capital T. Okay, the solution is stable if this V and mu is a unique solution. This a trivial solution is a unique solution to the linearized system.
Okay.
And stable solutions are locally isolated. Like you can always find a ball. There exists a ball, and inside this ball there could not be any other solutions. So they are separated from
the trivial one. Okay. Okay. Thank you.
And so if UM is a stable solution to the MFG system, then one can get the following estimate. This was not shown by me. It was from the paper of Briani and Cadillac. I'll be using this estimate. Okay, so these are just like estimates for the linearized, for some kind of linearized system. So the way I will be using this is to write the equation for V, which is UN plus 1 minus U. U is a stable solution. Okay, and rho is MN plus 1 minus M. So okay, and I will be working with the equation for V and rho, the system of equations. Okay. Well, important thing here, if solution is not unique, so it's not possible to prove for global convergence, obviously. So I'm showing local convergence. If I'm starting near a stable solution, then I will be going there if I use either SPI1 or SPI2. Here, the proof would be for SPI2. For SPI1, it will be completely similar, so I just don't talk about it. Okay. Well, the strategy of the proof would be to get some kind of estimate, which looks similar to Frank roof. Okay, I have a square term. Okay, so the point is that if I have a capital N0, which is large enough, then I can start to iterate, and I will always remain within a small ball near the stable solution. Okay. Well, it's okay. Let me don't go into too much detail, but anyway, so I have a small eta hat and I have a large N0. Okay, from there I will always be staying within a very small ball near the stable solution. Okay, then I say if N0 is already fixed and the eta hat is fixed, and that can show that if I start, from the first iteration, very close to the true control or the policy, which is can be obtained from the stable solution, and then in finite number of steps, I can always go there, remain in the ball. Okay, and finally I can show convergence. So that's I split into two parts and just use some estimate results. Okay, it's a bit tedious calculations. Discretization. Okay. I think I'm running out of time, but anyway, so let me skip to go to the important part. Okay, so I'm considering global couplings. So these are, so I use the integrals to, I use the sum to replace integrals. And I use two-sided policy, or the drift Q. I have to take the two-sided policy, and also because I'm doing that, I can recover the joint structure on the discrete level. So you can see this integration by parts is replaced by the summation by part, and so on. Examples. If I solve the system above, it's actually in the discretized form below. So if I say I'm using finite difference scheme and smooth polarization to solve the MFG system, I'm actually solving the system below, not above. But I believe the convergence can also be shown for the discretized system. Okay, I did not do it in the paper. I will do it, but I strongly believe it is true. Okay, so this is a discretized form of the SPI1. Okay, I just explained the key. The key point is that when I do averaging, I have double-sided policy. Okay, Q is double-sided because I want to use monotone schemes, and also the increased Auger flux. Q is double-sided. That's why when I take average, I also average separately on the two sides of Q. When I do smoothing, I have to maintain the two double-sided structure of Q, and this is SPI2, same thing. Okay, I know this slide is terrible, but you get the main idea that I have two-sided policy. When I do averaging or do smoothing, I keep this structure. I cannot break it, and okay. For the numerical simulation, okay. Well, I prefer to work with from -1 to 1. Well, this example is with Newman boundary condition, and I use a kernel, and well, one can derive using similar method from the book of Camon de la Rue. You can derive this coupling from the potential. There's a potential structure here. And also the coupling satisfies the monotonicity condition, and I can draw M and U. Okay, let me explain a bit here. So as Matteo explained to me, sometimes it's a bit delicate to say that the algorithm is converging. If I just show Qn and Qn plus 1 is going close to each other, becoming close. Because if I'm doing smooth polarization, of course they are going close. The same thing with fictitious plane. So what I'm drawing here is a picture of Q1 and Q bar n going close, or Qn and Q hat n is going close for SPI1 and SPI2. Okay, maybe this is the more convincing that the algorithm is actually converging to the correct solution. I can do just 1 minute. Okay, I can use some other. I can change the parameter of the examples. Okay, I do not get into details, but by changing the parameter, I'm trying to say that with these new parameters, it's actually more difficult to get convergence by other methods. I don't want to show that but okay, but with smooth polarization, it's also difficult. But what you need to do is just to wait long enough. For example, instead of 50 iterations, let's wait 150 or 250. It's going to converge. So this is we can show global convergence, meaning that theoretically it's going to converge from any initial guess. And in reality, it's similar. If we have a not very good guess, then the convergence would be slower. It takes more time, but it will still converge. So that's the point. Okay, for possible future works, I think it'll be interesting to see how this methodology is related to online mirror descent or polytext, which is different methods for smoothing the policy updates. And also what happens if we are studying finite state MFGs. If the policies are randomized, okay, we cannot use a simple averaging because the definition or the meaning of policy is no longer the same as a PDE case. And finally, I think applications in mean field gain of controls would be very interesting because it's intrinsically non-local in general. And also you're working with the couplings between controls. So it's natural to update controls separately from other things. That's all. Thank you very much.
Nice. Thank you very much. It was a nice talk. Are there further questions or comments? I have one quick question on the plot you were showing at the end.
Okay.
Maybe you said it, but so here it looks like it starts very low and then go up and then go down again. Is it because at the first iteration there is just I don't know, the distance is 0 at the first iteration?
Yeah.
It's just the first point, right?
Exactly. Q0 and Q bar 0 is the same by definition.
Yeah.
So it starts from 0. Yeah.
Okay. And then do you know that, maybe you said it, but I missed it, like, do you know that it has to be monotonically decreasing, or could it be like going up and down? Like, okay, let's forget about the first point. But then, the curve here, it looks like it's always decreasing, but could it go up or down, etc.? Or do you have a kind of monotone decay?
I have, I cannot, and I did not think about proving it, but I have not encountered that in examples. I have not observed that in concrete examples.
I see. Okay. Okay, thanks. I think there are two other, Thanos, do you have a question?
Yep. On the same slide,
Okay.
I was curious, how much is it computation time? Like, does it take like per iteration, or like to run all the iterations? Like, how much time would it take?
Well, I can a few minutes, like very fast.
It's a few minutes. Okay, it's quite fast. I was expecting much more.
Well,
you were doing finite difference in BDs, I would expect a bit more, but
these are one-dimensional examples. So it's natural, it's fast. So you see that I put so the iteration time depends a lot on the time horizon capital T. So here, for the examples, I used capital equals to 1, which okay, if you put capital T equals to 2, it will be much slower. But in general, these kind of examples, the convergence is very fast. Like, okay, with other method, maybe you need less number of iterations, but the convergence, in terms of time, is similar. So we also worked on mean field gain of controls. There are concrete examples that Song was doing, but for the some other examples, it takes a really long time. So it depends on the concrete case, each individual cases. Yeah.
that's all from me. Thank you very much.
Rinal, do you have a question?
Yes, I did. Thank you very much, Thomas, for the very interesting talk. I had two naive questions. The first naive question is on the method. Since you have these assumptions on the Lagrangian, what happens? Wouldn't it be like easier if instead of simulating the policy, that is the feedback function, on time and space, you instead did that only through time by taking, instead of x, xt, the actual state of the agent, such that you just have to you just have to simulate a trajectory because you have like nice assumptions. So have you tried it? I guess that's my question. Have you tried to do this analysis by simulating only through time, by taking, instead of an X on a grade, just like X of T?
I don't know. I think you are referring to some stochastic method or some sampling. But here it's just PDE. So the policy is just bounded vector field.
Yes, but you also have the SDE, right? So you okay.
No, okay. The SDE is just for the background. It's just motivating the model. So I'm only working with PDE. Okay.
Okay. Thank you.
So you're welcome. So I believe it will be very interesting if one can, find out what happens if we use a similar method for SDEs, for example, using samplings and so on. I believe it might be possible, but it's not the same thing. It's just PDEs here.
Okay, thank you so much. It was a naive question. The other naive question is the stable solutions. I don't know. Like, I'm interested in non-uniqueness, and it's quite the first time that I made this solution actually. So thank you. That's good for me. My question is, how does this solution relate to like the payoff? Do we know if the stable solution is somehow among the many solutions, has minimum like cost for the payoff or something like that?
A stable solution is a minimizer. For that, I think you can just check the paper by Briani and Cadillac, which is here. I go to the references. So they explained what the meaning of. Okay, this is the second reference.
Okay.
So they show that solutions, stable solutions do exist, and also there are solutions which are not minimizers. So they have concrete examples. And I'm not claiming to doing anything innovative with stable solution. I'm just showing that local convergence to stable solution. With the method that I developed, and the method was also based on this paper. So in this paper, they showed that fictitious play would converge locally to a stable solution. So here I'm just using similar method to show that smooth topology iteration would also have local convergence. Okay.
Thank you so much. Thank you.
You're welcome.
Okay, nice. Thank you. So, well, if there are no further questions, thanks again for the nice talk, and thank you everyone for attending.